Have you ever wondered where we get all that detailed information about reactions and molecules that we learn about in chemistry class? The answer is highly accurate calculations for electron structures and reaction mechanisms. These calculations involve simulating molecules and reactions according to the quantum mechanical rules that we learned about in class. Most specifically, in order to be the most useful, these calculations need to accurately account for electron correlation. As you remember from class, accounting for electron-electron interaction makes Hamiltonians and energy calculations complicated. This led to approximation methods such as the Hartree-Fock method and density functional theory. As the number of atoms to account for in a reaction increases, computation times exponentially increase. These complex computations quickly become out of reach for our current computers. In fact, just around 100 correlated electrons have proven to be too much to get accurate calculations for reaction mechanisms. And the truth is, 100 electrons really isn't that many. So what do? Well, now that our classical computers have failed us, we must turn to something new: quantum computers. Quantum computers are devices that harness the power of quantum superposition of states, just like the superpositions that we learned about in class, to perform calculations exponentially faster. While classical computers, like the phone in your pocket, use a discrete two-state system to perform calculations, like the binary 1 and 0, quantum computers use a superposition of these states in order to increase computational power. It's proposed that pairing the computational power of a quantum computer with classical supercomputers can exponentially decrease computation times for simulations of strongly correlated electron systems. This helps in the elucidation of more complex reaction mechanisms. In elucidating reaction mechanisms on quantum computers, quantum computing is proposed as a solution for elucidating the mechanism behind biological nitrogen fixation by the enzyme nitrogenase.
Okay, what is nitrogen fixation? Nitrogen fixation is a process where atmospheric nitrogen is converted into organic nitrogen compounds that are used for various biochemical processes. In this case, atmospheric nitrogen is converted into ammonia through this enzyme called nitrogenase. What happens is that the process is accompanied by 16 ATP molecules during hydrolysis and the co-formation of one H2 molecule. What's so interesting about this process is that nitrogenase contains a metal cluster called the iron molybdenum cofactor, where conversion of N to ammonia actually occurs. What happens is that the mechanism goes through a series of protonation and reduction steps where phenolico hydrogenase the N2 substrate. In the present day, we make 3% of the world's supply of fertilizer using nitrogenase. The majority of fertilizer is made with the Haber process, but nitrogenase makes it at a very low energy cost. A better understanding of nitrogenase reaction mechanisms will make it easier to use these low energy methods.
To start this process of elucidating a reaction mechanism, we first need to establish potential intermediate states to evaluate the energies of. To start this process off, they found two potential intermediates using density functional theory. The next step here is to calculate the associated energies with each of these configurations. Current classical computers would not be able to handle such massive calculations due to how much correlation you have between all of the electrons in this system. This is why quantum computers are such an attractive option for this, because our current classical computers just make this problem simply impossible. The goal here is to approximate how long a quantum computer would take to actually run these energy calculations. The researchers first needed to start off by defining methods that they would actually use to run these energy calculations. They found three to do so: serial, nesting, and par. Starting off with serial, the serial method uses a simple quantum computer with a simple algorithm. Nesting uses a few more qubits on the quantum computer and uses parallel programming for some parts of the calculations. The final method, programmable ancillary rotations, or PAR, utilizes multiple quantum processors all running in parallel. After establishing all three of these methods, the researchers would then go and run all three of these approximations for both of the structures that they were testing and for both quantitative and qualitative results. The PAR method had the fastest results, But with such an absurd qubit count, it's simply not possible for us to approach this method in the modern day. The nesting and serial results had a much more modest qubit count and are much more approachable in the modern day. On the slow end, serial could take as much as years to finish these calculations. But with a fast enough supercomputer, both serial and nesting approaches could complete these calculations in months to even days. This is a huge improvement over classical computers that simply cannot approach this problem.
So as the computing power of today's quantum computers approach or even exceeds that of the classical supercomputers, quantum computers can be used to elucidate reaction mechanisms in complex chemistry systems. Using biological nitrogen fixation in nitrogen gas, hydrogenase as an example, the paper shows how quantum computers can help enhance the classical supercomputer simulations used to explore these reaction mechanisms, significantly improve their accuracy and achieve so far intractable marks. Before this paper was published, quantum computing lacked practical applications. The paper shows the potential for quantum computing as the solution to computational chemistry problems. The quantum computer acts as an accelerator for the classical supercomputer during the simulation of two prototypes of structures of chemical in biological nitrogen fixation. This hybrid classical quantum computer for quantum chemistry type calculations that is used to calculate and correct this energy of intermediates is reduced from years to days through parallelizing calculations.